So, welcome all to our second lecture. And in this lecture, as I have promised in my last lecture or the first lecture of our this advanced control series, that I am going to discuss on some more mathematics and then we'll directly go to the subject. And before I start, or rather before you start watching or wasting time on this video, please make sure that you have certain knowledge about linear algebra, like what you have been taught in your undergraduate, means that first 1 year mathematics, that linear algebra part will be very much required, and I will shape my video in such a way that you do not need anything extra, but at the same time you need nothing less. Like if you have already means forgotten that whatever had been taught to you in that course of linear algebra, that vector space, please go and revise it and then come back again. Otherwise it is totally and means it cause wastage of time for you. Fortunately, as this is a flipped classroom mode, that I am not present, I will not be able to means notice your frustration, and that is also a benefit on my part. But it is advisable that if you have forgotten, that either you pick up any book of engineering mathematics. We just need the basic concept of vector space, not nothing very means like the math major type of things we do not need. And those who want more elaboration, they may be, go through that video link I have already shared of Professor Gilbert Strang from MIT. So they may go through that. Now today we will discuss about from what I left. Like I in my last video I discussed the notion of class C function. What is class C, C1, C2, C3? Like C, if a function f, if we define it is like, if we have a set K belongs to Rn, we call sometimes K is a domain of the function, and this K, how we define this K, I will tell more on that. K is non-empty, and also K is compact. By the word compact means it is closed and bounded. So generally what we do, we consider a bounded region around our origin, and it's quite often what we do is that it is symmetrically placed. For an example, you consider as if you have a three-dimensional coordinate system, and you take a football and you place the center of that football in such a manner that center of the football coincides with the origin of your coordinate system. Now, what is that origin of the coordinate system? If you understand vector space, then that origin is that origin also represent a vector, that is your additive identity, right? And a vector space must be symmetrical with respect to your additive identity. Otherwise, you cannot ensure the existence of additive inverse, that is also means required by the axioms that we define for a vector space construction. So now we define, now obviously when we are talking about placing a football such that football center coincides with the origin of your coordinate system, now the second obvious question is that what size of football you will take? A standard one or a kids plastic football? Yes, that is an important question of K, and on this domain K, and generally what we do, we take the help of Euclidean norm. If you are not, I will explain Euclidean norm later, but you can just, using your common sense, you can understand this is the radius of your football. Like if you take a toddler football, then the radius will be something, and if you take standard football, then the radius of that standard football is somewhat bigger, or means than that of your toddler's football. So obviously in that way you can consider that it is means ball whose origin is coincide with your origin. Sometimes it may happen so that due to some other purpose, we may consider this formation of ball around some other points, but the way we define it is always by means of the radius of that ball. Anyway, here it is not required for the present discussion that whether we place our ball at origin or place our ball at some other point. What is needed, that is the ball must be a proper subset of, means it's an n-dimensional ball. Like if you are having a 4-dimensional space and I am talking you to, or even if you find 4-dimensional space is difficult to visualize, your one means your circle is, if you consider, or a disk, better to say a disk, it is also a disk with means can be considered as a means subset of a ball. But here when I am talking about K belongs to Rn, it is better to consider a 3-dimensional ball, not a disk, right? Obviously a disk also belong to Rn, so R3, so you can say in that way, but it is better when we will start discussion that you consider in this way. Now what is there, what I am going to tell you, that what we define a function if that is belongs to the class C, like f is a function. This statement implies what? F is a function from Rn to R, and in addition this one, whatever be your independent variable, be it x, be it t, that with respect to that, when you take this exists, right? Now obviously this means this when I wrote it, it's like that. Instead of writing, let me just go back so that you can collectively, yes, it is like this, right? In this way, obviously here L is less than is equal to K. This is the definition, right? Now what I am going to state here, that if f is a function defined in this way, then two things we can two conclusions we can draw. One, f is two, f These two are very important observation, because when we will study lab now, uh, probably in the month of March, you have to be very means means you will find a heavy application of this concept, a compact set and uniform continuous function that attains means minimum and maximum on a compact set. Now, in the next part, I will like to represent that a function that is from one like a function that will define in this way. Right. So what we will do, we will consider a subset D belongs to Rn, and this function will define only on D instead of Rn. Then what we can write, like this can be viewed as a vertical concatenation of all in m number of functions that are having mapping from n to 1. Previously Rn to R, that is a function that maps from n dimensional to 1 dimension. Now when we are having a function that is mapping from n dimension to m dimension, that is basically we can see that this is a concatenation, or means this is a group of m functions where individual are mapping from n to R. So we can write it like this way. Where individual function is doing this, and here I is equal to obviously and in that case what we say so basically what we are trying to say, now what we can get, like that same extension, if we have a class k means like continuous function of order k, then we will have that actually indicates what happened. So I hope this is clear. Now we'll go to initial value problems. So what is there in initial value problem? Let us again consider a domain D that belongs to Rn plus 1. let this domain be please be very attentive when I write open on empty, open connected, compact. Compact means closed and bounded. All these things are very important for us, right? We call this Rn plus 1 is the t comma x space, and elements of Rn is like x is equal to, well, now here it is I am following a book by that author name is he is an IEEE Life Fellow, Panos J. Anzaklis. Anzaklis and Mitchell, their book on linear system, they have followed this notion. In some other book, some other author, both are true, means at least true for and valid for linear system. The other author, what they do, they represent it as a form of Cartesian product of time with the set Rn. And here what we have done it like Rn plus 1. So both the representation, it is just a different, means for engineers mathematics is a tool and we just use it to ease our work, ease our representation, to find a solution that is of more useful and generalized and applicable without much modification in a real problem. So we are doing this here. So this is x is equal to this. Now in addition, if we consider that if I where I is equal to I and 1 is you will get confused due to my poor handwriting. Is a function of t. Let this is a representation right. So this denotes the nth derivative. So when n is equal to 1, we we write it like xi dot. You are already acquainted with all this. Now what we will be doing, we will call this is very important term, that is system of equations that is given by oh, right, where I is equal to 1 to n, right? Now this is a system of n first order ordinary differential equation. So here what we will do, now we will try to investigate the solution of this system, the solution of the above equation. We write it, means what do we mean by the term solution? This is very, very important. By solution we mean n continuously differentiable functions, that is from just a minute, let me have some coffee. So we have n continuously differentiable function phi 1 to phi n defined on an open interval j all these public t phi 1 t means all these they belongs to D. So what we are trying to say, that J, it is an open interval. Why open? That will also come, that why it needs to be opened. Then we are having a function phi that is from C1 J to R. Now what we are having here, it is very important to note that obviously when I am writing phi, it is phi I basically I am trying to mention. What we are having here, if you ask me to write it in a mathematical way, then it is simple thing, that is time differentiation of this phi I yields this one or means you can write for all I or better to write it not in this way, rather to write it them all of them individually. See, actually, although this you will find this is closely having a close connection with our control system solution, but as of now, I just intentionally left or means intentionally avoid that uttering of the terms control or system here in this context. Once I will start control, then you will see that how this kind of abstract description or abstract mathematical representation will make some sense and also get some relevance with our topic of discussion, right? Now with this, this is our this is for I is equal to 1 to n, and this is true for all t that belongs to where? Belongs to that interval j. So basically we are just picking up a chunk of time, and within that time chunk what we are observing that these are the functions, these they are. Now why we are doing so? Because we want to establish some relation with the initial value to the final value. Obviously initial value and final value, these two depends on where you start and where you end, right? So it is very important. Now let us consider that the initial point. It is very interesting to note that you may ask me like means what is your common idea that do we need to mention the means why do we need to mention all these, like these are also zero. My handwriting is poor, so you may get confused that I am writing O, but that is not the case. So this is initial time, and these are the initial state. So obviously one question can comes in your mind that what is so special, like why do we need to write initial time and initial state? Can't we just write it only by means of initial state? Because it is quite obvious that the point where you start, even if you forget about initial point, initial time, think about a particular differential equation. We are say we do not know what is control system, just means keep it aside, control engineer. Just consider that you have a differential equation, a plain first order differential equation. Now what does this mean? Say this differential equation is something like this. So why do we need, say, instead of having this is an n-dimensional case, let us make it more simple like one dimension. So it is obvious that when we will start, that is t naught, and at that time, what will be the value of this x? That will be x naught. So why do we need t naught and x naught, both of them? I would like to hear this answer from you. More specifically, again, I am telling you the question that it is clear x t naught is x naught, then why do we need T naught, X naught, both of them to specify our solution? And I hope you still remember those kind of true false question that came in your E2001 end semester and E2002 mid semester. So in order to answer this kind of true false question, this type of concepts are very important. Now, if this is the case, then the initial value problem, what we termed as initial value problem, that is associated with that set of equation right? Now, this is a set of functions is a is a solution to the initial value problem. This is a initial value problem if what it is going here. Just a minute, I just want to copy this equation. is a solution of, right? So this in functions is a solution of, means we'll consider them as a solution to the initial value problem if this is a solution for this set of equation on some interval. That interval j we already know, it is an open interval, and we have to ensure that, oh god, and we need to ensure that this similar thing means you have already done in it during your uh, basic engineering mathematics. When you used to solve differential equation, you used to solve the problems of boundary values. So these are the things that is like checking the boundary values, nothing else. You are means putting some limiting times and then check whether your solution match with that. So it is in some other way. Anyway, so in dealing with system of equation, we always find it to take help of vector space, and that is why what we write it like x is equal to x n transpose x naught is equal to transpose oh transpose like this is a collection of, sorry, all the, for all I is equal to 1 to n. So all these are the things that we know, and with this the notation above that one, this particular equation can simply be represented like it would be good if I could make it bold, but because these are just a single dimensional thing, but this one is an n-dimensional vector. So make sure you identify the difference, and obviously this has to be true. Now it is your like, for interested reader, I would like to give one assignment that to prove the initial value problem can be written like this equation. Fine. Now we will go for periodic means classification of differential equation. So now we will classify a few systems like first of all uh, let us start with a system that is governed by the equation x dot is equal to f of t comma x. For the time being, we will not consider that whether a solution will exist or not, and even if solution exists, whether that will be unique in nature or non-unique. We are assuming that we are dealing with a linear system, even if there exist a few category of such system, like if we can have this one is identically equal to this triple equal sign indicates identically equal to f of x in a simply stated, if the rate of change of your derivative becomes independent of time, or simply stated the system is not time varying or time invariant in nature, then we say it is an means autonomous system. We can write it like x dot is equal to f of x. Well, just now in this context, I would like to make one thing very clear, that uh, it this sort of representation right now we are from mathematics, we again started means considering control engineering case. So while we are describing this in this way, like x dot is equal to f of x, it may trigger you a notion that this system is a force free system, or it is independent of, or means not governed by any input, but which is not the case. Like what I am trying to say, it is the case that like unlike the problem of optimal control, what is optimal control we will discuss later. Just for the time being, you keep it in your mind that optimal control, and in your basic control class, I'm not sure, neither it was mandatory. It may happen that Professor Noskar might have discussed on that what is different error, like integral absolute error, integral square error. So all this minimization of error also gives certain performance index, and in that early age in 1940 1950, people used to do minimization of those error depending on their objective or requirements. So that is the case. That kind of problem is known as optimal control. So in that optimal control, we always look for an optimal input, where input is supposed to vary, but otherwise what we can do here is that for other system, we study the system performance under a fixed input function or non-fixed function. Now again, don't get confused with the notion of fixed function and constant function. Fixed function means if it is sinusoidal, then we will study it with a constant sinusoidal excitation. It's like that. If it is a step, I will consider it with step. That doesn't mean that it is always constant. But what is there, that if our system is better to say that for a known fixed function, then what we can represent, actually this means, to be very honest, the most generalized form of equation should be like this. And in that case, Your f, we can write that fx belongs to another domain, say d dash belongs to d dash. This belongs to d dash, where d dash is what is p, or in some other representation it is written like this is not x, this is Cartesian product. So this is one form of representation. In our form of representation, in that case it can be n plus p plus 1. Previously it was n plus 1. That was for force free system. But this representation, my point is that this autonomous system or this term is still valid with system with input, with a fixed known input. This is still valid. So don't get confused, right? Uh, and moreover, it is interesting to note that this system is like it's autonomous if it is not dependent on time, right? Now, so for autonomous system, we can write it like x dot is equal to f of x for your means you the 2 points for autonomous system. Well, now you are having this is autonomous system of first order differential equation. Now you can have another kind of system, that is if we have and in addition if and this is true for all t comma x belongs to D, then this system can be written like x dot is equal to f of t comma x f of t plus t comma x, like it is time dependent and time dependence is periodic in nature. Then we can call such an equation as periodic system of first order equation. The smallest such t greater than 0 for which this equation holds good is called the least period. Well, now now if further we can write this f of t comma x is equal to where this a is an n cross n square real matrix, and this one is like all these element of A are defined, and A is piecewise continuous on T interval J. Remember, T belongs to that interval J. So what we can say that this is a linear homogeneous equation. We say it is a linear homogeneous equation. Now if we have something like that same thing, but in addition it will become then we'll call it linear periodic equation or linear periodic system. In addition, if it becomes then it will be linear non-homogeneous system, and if you have homogeneous and also this GT identically means 0, then it is linear autonomous homogeneous system. So if you are having this, then it is linear autonomous homogeneous system. Again, I am telling you that there is means it may give you a confusion that the system is like having no input, but it is not always the true, right? So it is, but here in this case it is force free obviously. So this is a case of linear autonomous homogeneous equation. In our next lecture, we will see that what is the notion of equilibrium point, what do we mean by equilibrium point, and how we can linearize system around equilibrium point. What is the objective of linearization? Like, see, here I am not here to deliver lecture on linear system or non-linear system. This course is advanced control system. So your perspective related to control engineering should be broad enough, should be you should have a more in-depth knowledge in that subject. Means if you are at all interested for learning this subject, you must have a in-depth understanding that in reality no linear system exists, what I discussed in my last discussion session also. But what we can do is that if it is almost linear and that the deviation from the nominal model is negligible for its course of operation, and the nominal model itself is linear over that range of operation or over that operating period, then we can say that this system is linear in nature or linear system. And for that we will have all these kind of analysis we do, like for their steady state. Even we can go for drawing phasor diagrams. All these things are possible only when you consider the system is linear time invariant system. But that kind of system means if you are 100% honest, then you will never find this kind of system. But it is always a compromisation between the means ideal systems and reality, and also what we could afford and what we would be able to gain by means taking certain burden. Like why I am saying all this to you, try to understand one thing, that you are free to consider the most complicated model of a, and meticulously you can conduct experiments to find out a model, but that cumbersome model may not be suitable for designing any control law which you have studied in your last semester. Also in this semester you are going to study a few. Anyway, so in our next video we will be discussing that equilibrium point, and in addition that what is the significance or impact of equilibrium point, how we can linearize our system, and how means how to generalize it. And then in our next lecture we will means after covering that equilibrium point we will go to discussing about our solution of the system, right?